This paper studies the issue of recurrent language models generating infinitely long text sequences with zero probability. This paper is called Consistency of Recurrent Language Model with respect to incomplete decoding. It's from Xin, Velek, Kulikov, Kim, Yuan, Zepang, Cho. It's year 2020. And abstract is following. Despite strong performance on variety of tasks, neural sequence models trained with a maximum likelihood have been shown to exhibit issues such as length bias and degenerate repetition. We study related issue of receiving infinite length sequences from recurrent language model when using decoding problems. To analyze the issue, we first define inconsistency of the decoding algorithm, meaning that the algorithm can yield infinite length sequences that have zero probability under your model. We proved that the commonly used incomplete decoding algorithms, greedy search, beam search, top case sampling, and nucleus sampling, are inconsistent, despite the fact that the recurrent language models are trained to produce sequences of finite length. Based on these insights, we propose two remedies which address the inconsistency: consistent variants of top K nucleus sampling, and self-terminating recurrent language model. Empirical results show that inconsistency occurs in practice and that the proposed methods prevent inconsistency. Our main finding is that a sequence which receives zero probability under a recurrent language model's distribution can receive non-zero probability under the distribution induced by a decoding algorithm. This occurs when a recurrent language model always ranks the sequence termination token outside the set of tokens considered as each decoding steps, yielding an infinite length zero probability sequence. This holds even whenever the decoding algorithm is incomplete, in the sense that the algorithm excludes the tokens from consideration at each steps of decoding, which in this case for common methods such as greedy search, beam search, top case sampling, and nucleus sampling, which is the case under these. We formalize our main finding using a notion of consistency, Chen 2017, whether a distribution assigns probability mass only to finite length sequences, and prove that the consistent recurrent language model paired with an incomplete decoding algorithm can induce an inconsistent sequence distribution. Based on the insight that inconsistency occurs due to the behavior of the termination token under incomplete decoding, we developed two methods for addressing inconsistency. First, we propose consistent sampling methods, which guarantee that the termination token is not excluded from the selection during decoding. Second, we introduce a self-terminating recurrent language models, which ensures that the termination token is eventually ranked above all others, guaranteeing consistency under incomplete decoding. To empirically measure inconsistencies, we decode sequences from trained language model and measure proportions of sequences with lengths far exceeding the maximum training sequence length. They do experiments on big text 2 datasets suggesting inconsistency occurs in practice when using incomplete decoding methods, while proposed consistent sampling methods and self-terminating model parameterizations prevent inconsistency and maintain language model quality. The theoretical analysis reveals the defects of existing decoding algorithms, providing a way to develop future models, inference procedures, and learning algorithms. We present methods related to sampling and model parameterization, but there are more directions which we leave to the future. We close with direction related to the sequence level learning. Okay, let me go to the conclusion, and then we're gonna do another round with going more into depth. Conclusion: we extended the notion of consistency of recurrent language model put forward by Chen 2017 to incorporate a decoding algorithm and used it to analyze the discrepancy between a model and distribution induced by decoding algorithm. We propose that incomplete decoding is inconsistent and propose two methods to prevent this: consistent decoding and self-terminating recurrent language model. Using a sequence complication tasks, we confirmed that the empirical inconsistency occurs in practice and that each method prevents inconsistency while maintaining the quality of generating sequences. We suspect that the absence of decoding in maximum likelihood estimation as a cause behind this inconsistency, and suggest investigating sequence level learning as an alternative in the future. So that's all the juice, all the spice of the papers that must flow. I will continue in more depth in another round right now. If you're planning to exit, then don't like these videos and never subscribe. Yeah, of course, I'm joking. So now I continue. Introduction. Neural sequence models trained with maximum likelihood estimation (MLE) have become a standard approach to modeling sequences in a variety of natural language applications, such as machine translation, Bahderao et al. 2015, dialogue modeling, Vinician 2015, language modeling, Radford 2018. Despite success, MLE-trained neural sequence models have been shown to exhibit issues such as length bias. 2016-2019, and degenerate repetition, Holtzman 2019. These issues are suspected to be related to the maximum likelihood objective local normalization, which results in a discrepancy between the model's distribution and the distribution induced by decoding algorithm used to generate the sequences. Lafferty 2015, Andor 2016. This has prompted the development of alternative decoding methods, 2016 Wu, Holtzman 2019, and training objectives, Murray, Chiang 2018, Velek et al. 2019. In this paper, we formalize and study this discrepancy between the model and decoding algorithm. We begin by formally defining recurrent language models, family that encompasses neural models used in practice, such as recurrent neural networks and transformers. Next, we formally define decoding algorithm, a function that induces a distribution over sequences given recurrent language model and context distribution, which is used to obtain probable sequences from a model. In this paper, we show that the distribution induced by a decoding algorithm can contradict this intended use. Instead, the decoding algorithm may return improbable, infinite-length sequences. I read this part already. Determination token, right? Background. We begin our discussion by establishing background definitions. So sequence, or the collection of items, finite vocabulary, piece and token. Context distribution. Context distribution is a probability distribution defined over set C, and element C is called context. Each model we consider generates a sequence conditioned on context information, such as prefix in a sentence, completion. Could you consider this? We define context distribution. Recurrent language model. A recurrent language model is a regressive model of a sequence distribution which each conditional probability is parameterized with a neural network. Importantly, we assume that all tokens in a sequence are dependent on each other under a recurrent language model. This allows us to avoid cases in which model degenerates to Markovian language model, such as n-gram model with finite n. Recurrent language model. A recurrent language model P of theta is a neural network that computes the following conditional probability at each time step. So it is a probability. Okay, I'm not gonna read every equation, but this one is sort of like a softmax of a product of vector u with h plus some bias CV, I guess, where ht and h0 and uc and theta are parameters. A recurrent language model thereby computes the probability of a sequence y by conditioning on the context and doing product of the conditionals step by step. Practical variants of recurrent language models differ by the choice of transition function f. For example, Vashwan in 2017, right? Those are transformers. The use of softmax 1990 implies that every unique token in the vocabulary is considered at every location of a sequence. Under the conditional distribution of recurrent language model, every token V is assigned a positive probability. This implies that every token has probability bigger than 0, less than 1. In addition, it follows that finite length sequence probable by recurrent language model under any context. Yeah. Okay. So here they say that it implies that it follows that any finite sequence is probable by a recurrent language model under any context. Under any context, it is probable that the sequence may be finite. Okay, decoding algorithms. So I'm gonna skip these, right? Everybody's probably familiar. I'm just gonna read the definition of the decoding. Decoding algorithm is a function that generates sequence Y given the recurrent language model P and context. And then distribution. Okay, decoding. Stochastic decoding. Sampling asymptotically biased can be used for finding ancestral sampling. Yeah, actually, I'm gonna read this one. I'm interested. I'm no big expert. Ancestral sampling F generates a sequence from recurrent language model P given the context C by recurrent language sampling P YT under T US. So the recurrent language samples from conditional distribution and okay, so I guess it samples fully using all the probabilities, every tokens possible. In order to avoid high variance, two approximate stochastic decoding algorithms have recently been proposed and tested with recurrent language models. Top K sampling considers only a subset of K most, we are familiar, and the nucleus considers only a minimal subset of most probable tokens whose total probability is higher than the predefined threshold. Yeah, so you know these. Then we have greedy decoding, always takes the most probable. And then beam search, which operates on level of partial sequences or prefixes. Where we have beam search. Beam search with width k generates a sequence from a recurrent language model P of theta by maintaining size case prefix set of p top, starting with p top equals empty set. At each iteration, beam search forms a new prefix by expanding the current set, where raw views concatenation, then choosing the k highest scoring elements. Any ending with sequence is restricted from being expanded further and is added to a set S. Beam search ends when S contains k sequences and returns the highest scoring sequence in S. Okay, so the beam search builds those sequences and exits always when one of them ends, right, gets the end of sequence, and then from all of them selects the best one, the most probable one. So incompleteness. Other than ancestral sampling, the decoding algorithms above are incomplete in that they only consider a strict subset of the full vocabulary at each time, aside from trivial case where k is the size of a vocabulary. Incomplete decoding. A decoding algorithm is incomplete when for each context C and prefix Y there is a strict subset of a vocabulary such that the sum of the probabilities over that subset is equal to 1, right? Consistency of decoding algorithm. May assign positive or infinite length. We extend this definition for different content consistency. A recurrent language model is consistent under a context distribution where so it's consistent. So the language model is consistent when the probability of infinite sequence is 0. Otherwise, the language model is inconsistent. If the recurrent language model is consistent, then probability of size of a sequence is infinity, is 0 for all contexts. Okay, yeah. So they defined it. So previously, it was under a specific context. For an improbable context. So if a language, so this is a lemma. If a language model is consistent, then probability under any probable context. Okay, so the recurrent language model is consistent under context distribution. Okay, it's consistent, it's uniformly bounded. A recurrent language model is consistent if H is uniformly bounded for some P. Proof sketch. Next, we establish practical condition under which a recurrent language model is consistent. Proof sketch. Although this condition is practical because layer normalization under bounded activation functions result in bounded H, we should show that even if the recurrent language is consistent, the decoding algorithm may produce an infinite length sequence. We formalize this discrepancy using the consistency of the decoding algorithm. Consistency of a decoding algorithm. Decoding algorithm is consistent with respect to a consistent recurrent language model P under a context distribution probability of C if the decoding algorithm F preserves consistency of the model P, that is, that the probability of infinite sequence is 0. So they say that obviously you can have a recurrent consistent model, but if you use inconsistent decoding, you can still get inconsistent. Inconsistency of incomplete decoding. Okay, lemma. A consistent decoding algorithm with respect to a consistent recurrent language model decodes only probable sequences. That is then P for an approvable context. An incomplete decoding algorithm can be inconsistent regarding. Okay, I think I'm getting too much into the weeds here. I'm gonna speed up a little bit. Inconsistency of an incomplete decoding algorithm. There exists a consistent recurrent language model P from which incomplete decoding algorithm F that considers only up to vocabulary size -1 most likely tokens according to each time stat finds a sequence probability under P is a consistency where. Okay, I'm getting too much into the fixing the inconsistency. Consistent sampling algorithms. The proof of the inconsistency of incomplete decoding algorithms arises from the fact that end of sequence token may be excluded indefinitely from the set of top ranked tokens. We propose a simple modification to top K and nucleus sampling that forces end of sequence token to be always included in each step of decoding. This gives the condition for the particular model paired with decoding algorithm to be consistent. 4.2 self-terminating recurrent language model. Although these consistent sampling algorithms can be used with any recurrent language model, their stochastic nature may not be suitable for finding a single highly probable sequence. To avoid this limitation, we propose self-terminating recurrent language model. Self-terminating recurrent language model. A self-terminating recurrent language model computes the following conditional probability at each time step. So it computes 1 minus alpha of ht if v is end of sequence token Otherwise, it does the softmax multiplied by alpha of ht, where alpha of h0 is sigma of end of sequence token alpha h80 which is computed as the original language model. Underlying idea is that the probability of end of sequence increases monotonically. The model is consistent with when paired with greedy decoding. Greedy decoding is consistent with respect to any self-terminating recurrent language model. Beamsearch is also consistent with respect to any self-terminating recurrent language model according to similar argument, appendix B for proof. Empirical validation. The theoretical results on the existence of the model that results in inconsistency. It remains to be shown that inconsistency with respect to encoding decoding occurs with recurrent language models encountered in practice. Moreover, while the proposed consistent sampling methods and self-terminating language model can be theoretically guaranteed in terms of consistency, we must still check retain the language modeling quality. To do so, we perform two experiments using the sequence completion tasks. In these experiments, we use beginning as a sequence context, decode, not terminated sequences occur in practice. Show the effectiveness of the problems. Sequence completion, dataset, context distribution. Evaluation metrics, non-termination ratio. In each experiments, we report the mean and standard deviation of metrics across 10 different initializations. Unless specified otherwise, we report metrics using test context distribution since the trained, valid, and randomly generated consideration had similar results. Training, models, beam. Table 1. Non-termination ratio of decoded sequences with unsound decoding methods. So greedy. Okay, I'm getting too deep into this. Inconsistency of recurrent language models. In this experiment, we demonstrate evidence of inconsistency with incomplete decoding methods. Consistency, we evaluate the consistent variance of token nucleus as well as self-terminating language models in terms of consistency language model quality. Okay, self-terminating RNN. Okay, table 3. Example continuations using nucleus with consistent nucleus sampling. Prefix. He had a guest starring a role on a television. Nucleus. Television film, the website, with whom he wrote the title of the English Women Domestic Magazine. End of sequence. C nucleus. Film. I guess C nucleus is consistent nucleus. Film website, but he did not be a new sequel and end of sequence. Yeah, so they show here that they seem to exit faster, and yeah, you can still see sort of like repeated unknown tokens that still happens, but you get the faster exit. Actually, I'm not seeing anything particularly special. Okay, so future direction. The methods proposed in this paper have focused on how to resolve inconsistency from the viewpoint of decoding algorithms or model parameterization. Another approach is to address the issue of inconsistency in learning phase. One interesting direction is to investigate whether the maximum likelihood learning is the cause of inconsistency. Given a training set drawn on the data distribution, the maximum likelihood learning solves maximum logarithm of probability, right? Conditional probability, where omega is a regularizer and lambda is a regularization weight. Inconsistency may arise from the lack of decoding in solving this optimization problem. Maximum likelihood learns to fit the model p theta using the data distributions. Whereas the decoding sequence from the trained model follows the distribution QF induced by the decoding algorithm. Based on this discrepancy, we make a strong conjecture. We cannot be guaranteed to obtain good, consistent sequence generator using the maximum likelihood learning and greedy decoding. Sequence level learning, however, uses decoding algorithm during training. We hypothesize that the sequence level learning can result in a good sequence generator that is consistent with respect to incomplete decoding. Alright, I already read the conclusion. So, thank you very much. Please don't like or subscribe. And I hope to